So there are two main types of carbonate acid treatments. So if we inject above the frac pressure, we get a fracture, right? And this fracture acidizing. If it's below the frac pressure, this blue region, then it is matrix acidizing, right? So in matrix acidizing, the flow is in the matrix. We don't crack the rock, and we get wormholes, which have these red features over here in the cartoon. And this is a block which we used, was about 3/4 of a meter block, and we drilled a small well at the center, and then we acidized it. And then after acidizing, we took a X-ray of that, and this picture is well. So I couldn't bring the whole block with me, but what I got was a wormhole. This was a core which was about 1 inch by 6 inches, and we was linear flow. We acidized it, right? And then after acid, we did a high resolution X-ray, a tomograph, and then we printed that tomograph image. So this is the 3D print of the wormhole that was created. So it is almost scale 1:1. So this are the wormholes that we would get in the formation also. So this was matrix acidizing. The other one is fracture acidizing. Here we inject above the frac pressure. We crack the rock. We also get wormholes. Here the wormholes are somewhat detrimental to the treatment because they contribute to the fluid loss and reduce the length of the fracture and reduce the fluid efficiency. Right? So we get wormholes in both cases. In matrix acidizing, the wormholes are the objective of the treatment. We want to get as many evenly spaced wormholes as we can. In fracture acidizing, they are somewhat detrimental. Okay. Now these are some more images of wormholes. This is a top view. It shows that the radius around the wellbore where it's wormholed. Yeah, so these are very high conductivity channels, and our wormhole radius, the radius of the wormholing region, is usually many times the conductivity of the matrix, right? The skin formula just reduces to just the wormhole radius over the wellbore radius, right? And the whole goal of this matrix acidizing treatment is to bypass the damage. So if you have a damaged well very near wellbore, you may have drilling induced damage, and when you acidize, we create wormholes that bypass the damage. Now I think I'll illustrate this with an example which is from this paper here, SPE 20623, which talks about a well which was producing 300 barrels of oil per day, right? They did a first acid treatment, and after the first treatment there was no change in production, right? So it was producing 300 barrels of oil per day. After the treatment, same 300 barrels of oil per day, and the treatment was clearly a failure, right? So they did a second treatment, and after the second treatment the well produced 3,000 barrels of oil per day. So an order of magnitude increase in production. Now my question to you is, the second treatment that resulted in 3,000 barrels of oil per day, is it success or is it a failure? So there are no wrong answers, so don't be shy. I mean, I just want to get an opinion. So people who think that the second treatment, one that produced, disappeared again, one that produced 3,000 barrels of oil per day was a success or a failure. So if they could kind of raise their hands for the people who think it was successful, that produced 3,000. So we have about half of the room. So let me ask the other way. How many people think it was a failure? Nobody, okay. But okay.
It might be a failure, depends on what type of fluid.
I think you're on the right track here. So it was a trick question, as you may have realized that it is a trick question. So there's no wrong answer. So people who said that it was successful, so yes, it was an economic success. From 300 to 3000, they had a large increase in production. The treatment paid for itself in very short time, and economically it was a successful, right? Now people who were thinking it was maybe a failure, because technically it was a failure, because the well, it's back again, okay. So the well is supposed to produce 6,000 barrels of oil per day, because the skin that we normally get after carbonate stimulation is -2, -3. So the first stimulation treatment did not change the skin. It was 30, remained 30. The second stimulation brought it to 0. But if they had designed the treatment properly, they should have gotten a skin of -2, -3, which would be a production of 6,000 barrels of oil per day, right? So technically it was a failure because they only got half of what they should have gotten, but economically it was a success, right? Value, and this is the cumulative wells with skin less than this value, right? So what this graph basically shows, that most of the wells after stimulation, so 80% of the wells after stimulation have a skin of -3 or lower, right? We're talking about the overall skin for the well, and overall skin for the well, most wells after acid stimulation is -3 or lower, right? So most of them are -3 to maybe 5, but there's some extreme cases over here. Now when people look at this kind of a plot, they think they're doing a fantastic job on acidizing, because I mean most of the wells have very large negative skin. But what this hides, and this kind of misleading, is I'm going to show that with an example, which is this one over here. And what I have here is the same well which was treated differently, right? So the same well, so the zones are the same. I have zone 1 and zone 2. Zone 1 is a high perm, thin zone, right? So it is about a Darcy and thickness of 10 feet. Zone 2 is a tighter and a thicker zone, which is about 10 millidarcy and about 100 feet, right? So normally, if the well is undamaged, you would expect the flow rate to be 10 to 1. I mean, zone 1 should produce 10 times more fluid than zone 2, because the ratio of KH1 over KH2, right? Now, let's look at the stimulation designs. So, this one over here, after the stimulation treatment, the ratio from zone 1 to zone 2 was 13 to 1, right? Both zones got stimulated, -3.2 and -2 over here. Now the second treatment, so the skin, the total skin from both these treatments is the same, -3.1. That means the production rate after both these treatments is going to be the same, right? It's just how the flow rate is divided, right? So this one was 13 to 1, this one was 91 to 1. Here what we have is skin of 30, which was not stimulated, and the zone 1 has -3.5 skin, right? Now, where do you think the oil is in this? I mean, the oil is mostly in zone 2, right? So if you stimulate zone 1 and not stimulate zone 2, zone 1 is contributing a lot more fluid. I mean, 91 to 1, right? So it's going to get depleted much earlier than zone 2, right? So what will happen if you're water flooding? You may have issues like scale formation. If the pressure depletes, you may have asphaltene precipitating out. So a lot of issues would arise because the carbonate stimulation treatment was not done properly in the first place. And if we are only looking at the total production rate at the well surface, right, they will look the same. Both have the same skin. But only when we do a flow profile, we get the difference between the two treatments. Now, which one is a more difficult treatment to design? This one over here, right? Because here we are injecting acid where it does not want to go. We want the acid to go to the tighter zone, but it wants to go to the high pump zone. So here, this is almost a no-brainer. Dump acid, it's going to find the first zone, go there, high pump, and it will stimulate it. You measure the skin, overall skin looks fantastic, and you move to the next well, right? So this one is, doesn't require a lot of design. The designs are very simple. Pump 75 gallons per foot, or whatever your favorite number is, and all the acid goes to zone 1, and zone 2, which is a skin of 30, never gets stimulated. Many times what happens is that the well is full of completion brine, and it's sitting over here. The acid comes from the top, finds the first permeable zone, could be a big fracture, goes into that, and never even makes it to zone 2. Right? So it never displaces the completion brine here. All the stimulation goes to zone 1. Okay? And over time, the differences are larger and larger, because when you come back and try to re-stimulate this well, because the first treatment was not correct, so you not only have to fight the big permeability contrast, now you have zone 1, which is high perm and stimulated, it has a negative skin, and if you come after maybe a few years, it is also low pressure. So you have worsened the problem the next time you come around. So you have zone 1, high perm, stimulated, and low pressure. So you have multiplied your problem made your problem a lot more worse by not addressing the stimulation design 1 correctly, right? Now, why I think that the carbonate stimulation treatments are under-optimized, and the main reason is that the success criteria that we have set for carbonate stimulation treatments, the metric for success is very low. So most common metric is a production increase. Now this survey over here, it was for 385 wells in this SPE paper, and with that criteria, a production increase equals success, most of the treatments, 90% plus treatments will be successful, right? So that is a very low metric for carbonates. But for sandstones, where the design is a lot more challenging, it's because of sometimes high temperature and acid-sensitive clays, if you get a treatment that increases in production, that's a good day. And if you don't design it properly, the success rate can be very low as 30%. So the criteria of production increase works for sandstones, but for carbonates, it's a too low a metric. Now, since once a job, an acid job is classified as successful, is labeled successful, there is a lot of resistance to change the design. In many companies I work with, they have the same acid recipe that they have been injecting for a decade or longer. Because they say we have a good program, we have acid injection, this recipe, and the production multiplies X number of times, and we don't need to touch it, right? Because that is very difficult to propose an alternate design when it's already classified as successful, right? But it takes some special kind of engineers to realize that the treatments are not under-optimized, and it takes a lot of courage to propose alternate designs. And this paper over here is from the Middle East here, and it documents such a case in which they had one acid recipe, they were using it in the field for decades, right? And they had a very good baseline because that's the recipe they were using for a long time. And the engineer looked at it and said he can do a better job. So he took a group of about 17 wells and changed the design. They were able to realize an incremental, additional 17,000 barrels of oil over these 17 wells. So they had a good baseline, what the previous design was doing. He changed the design for 17 wells, and these wells performed so much better that they got additional 17,000 barrels of oil per day. When the management saw this, they changed the entire field to this new design. So just a design that's been working for a decade doesn't mean it is an optimized design, because the evaluation was never done properly or rigorously. Right? Now, so if a production increase is not a good metric, it's a very low metric for carbonate stimulation, what is the good metric, right? So this paper over here, IPTC 13622, describes an alternate way of looking at it. So they look at, first they establish what is the maximum theoretical limit that the well can produce. They establish this limit, the maximum recovery or maximum production rate. And they look at how much of that production they were able to realize, which is the production increase. So instead of that, they look at how much production they missed, right? So instead of saying, okay, I missed, I gained X barrels or X recovery factor, they look at how much they actually missed, right? This is, to me, it's something similar to like the whole carbonate stimulation is similar to like a multiple choice exam, right? Suppose you have 4 questions on that exam, and you don't study for the exam and just come completely unprepared to the day of the exam and start randomly guessing. It's very difficult to get a 0 on that exam, right? Because, randomly guess, you get at least 25%. The only way to get a 0 is not attempt any questions, right? So carbonate stimulation is like that. If you don't design the treatment, just dump some acid, it's going to go to the high perm layer, you are going to get some production increase most of the time. Right? But if the treatment is engineered properly, you get a much, much larger production increase. And that's why if you have a limit, then you compare that, okay, if I just dump acid, no design, I'm going to get this much. But a good design will tell you that you approached closer and closer to the theoretical limit. So if you approach 90%, like for grading would be A, B, C, kind of 90%, 80%, etc., right? So that's a new way of looking at it, rather than just saying every treatment is successful because it is increasing production. Okay, now here are some of the treatment design elements, some steps that we go through. The first one is the treatment flow path selection. What I mean by this is we have to decide if we are going to inject the treatment through a coil tubing or through the production tubing. So we're going to bullhead or we're going to use a coil tubing. So whichever flow path you select, we need to pickle it. Pickling means that we take a mixture of hydrochloric acid and surfactants, we inject it and flow back, circulate, right, to clean the tubing of all the rust and gunk and scale and all of that may have in the tubing, right? So we don't want to inject that into the reservoir. So that's the first 2 steps here, flow path selection and tube pickling. The next one is pre-flush. So pre-flush is essential, especially if you have crudes which are asphaltenic. This creates a buffer between the reservoir fluids and the strong acid stimulation fluids that are going to inject next, right? So because some of them are not compatible, especially with asphaltenic crudes. And this pre-flush is a KCl, X%, or a mutual solvent, could be a solvent also, like a toluene or a hydrocarbon. After this, we go with acid injection. Acid injection is maybe 10 to 28% hydrochloric acid is very common. For high temperature, we use organic acid and chelants also. Then there's a diverter stage. And what we do is we repeat steps 4 and 5 for every 20 to 30 foot of formation. So if you have a 100-foot thick interval, you will have 5 stages: acid, diverter, acid, diverter, acid, diverter, like that, right? For every 20 feet. After that, we flush to the top of perforations. We don't want to leave live acid in the tubing. Then we flow back, or if it's a water well, water injector, we continue with the injection, right? So this is the sequence, and looking at that, we say, okay, what can go wrong? I mean, it almost looks like a cookie cutter kind of design. So what it hides are some of these challenges that I've listed over here. The biggest challenge in carbonate matrix stimulation is the placement of acid. How do I get the acid into the regions which are tighter, where it does not want to go naturally, right? And what makes the placement of acid difficult, the number one on the list is the heterogeneities. This picture is from Oman, I think, right? So these are natural fractures here, very large, as you can see, and you are trying to divert from these natural fractures to the tighter zones. So how do I get acid from here to the tighter zones? Now, the permeability contrast with natural fractures could be 2 or 3 orders of magnitude easily, right? Then a lot of carbonate intervals are actually very long horizontal wells, 10,000 feet. I think I've worked on wells which are 40,000 feet open hole sections, right? So how do I get acid all the way to the toe of the well? Very difficult, right? Then, since you have high perm zones, they produce a lot of fluid, and after some time they become depleted. So you have mature reservoirs, mature flow units, next to flow units at higher pressure, which are tighter. And the challenge is, how do I place acid into the tighter zones, which normally still have a lot of reserves, and not inject into the depleted reservoirs, which could be producing water and increase my water production, right? So these 3 challenges are mostly for placement of acid. And the next challenge, the biggest challenge I see, is the fluid selection. Which acid do I use? Which is the best acid for my formation? And the choices are quite a few, and they depend on mineralogy, temperature, rock type, and quite a few other variables. But unfortunately, the decision for selection of acid is only made by one variable, which is the price, which unfortunately the price can change between the lowest cost acid to the highest cost of maybe a factor of 2, 3, 4, right? But the acid efficiency, that how effective that acid is at stimulating a particular rock type, can be 1 order of magnitude difference or 2 orders of magnitude difference. So just by a factor of 2 in price or 3 in price, normally people miss out on a factor, an order of magnitude or 2 orders of magnitude difference in the acid effectiveness in stimulation, right? So they do themselves a disservice. Now, the third challenge I've listed is the simulation of the treatment, right? I've listed it as a challenge because from a technical perspective, there's a lot of chemistry and physics that goes on when we inject acids, right? So you have reaction, you have, because this reactive flow is creating those wormholes, right? And as it's creating these wormholes, you have that phenomena you're modeling. Then you have complex fluids. So you have emulsions, you have foams. There's multiple scale involved, right? And that is a lot more challenging, in my opinion, than, say, reservoir simulation, right? Because you have all of those challenges combined with the reactive flow. And if we look at the resource distribution between how much resources we dedicate to reservoir stimulation, you have the finest machines, supercomputers, clusters, a whole department devoted to reservoir stimulation. And if you look at a much more challenging issue, technical issue, which is carbonate matrix simulation, and there's hardly any decent simulator or a large computer that has been dedicated to that in most companies, right? So that's why this become a big challenge to, because if we could simulate the treatment properly, then we could see the things and hopefully correct them, right? Okay, here is a brief workflow that I think is one way of looking at all of these variables in a systematic manner. The first step in the workflow is the candidate selection, right here. Now, almost every new well you drill, right? I mean, you may do a fantastic job in drilling, but you'll still end up with, in the best case, a skin of 0, right? So a new well is by definition sometimes, a candidate. But the candidate selection is not just to assess that this is a candidate, but the big step in candidate selection is to establish the limit of how much the well can produce, the theoretical limit that the well can produce, which I'm going to compare my treatment with, right? So what is the theoretical limit for that well? So that's what we establish. Otherwise, every new well would be a candidate. Every well that has a positive skin is going to be a candidate. But the key thing is establishing the theoretical limit for the well. After that, we have a rock characterization part in which we identify what kind of rock type you have. The mineralogy is dolomite, limestone, is it a grainstone, is it a wuggy, is it fractured, etc., right? Temperature. Once we have these two variables in, I can go to a database, select the acid, right? Which acid is going to be the most efficient for this kind of mineralogy. After the acid selection, I pick up a diverter. Depending on the completion type I have, the permeability contrast, I pick up a diverter. Then I simulate. And I just said the simulation is not perfect, but it's important if you understand the gaps in the simulation, you can use the simulator as a good thinking tool, right? So you can try out designs, at least in theory, you can try to get acid into all the zones, right? Once you have a reasonable design, from the simulator standpoint, we execute the design. While execution, we can monitor it, or we can evaluate after the treatment. And this loop over here is critical, right? So we said our simulators are not perfect, but this feedback loop ensures that we have measured data from evaluation that we use to improve our simulators. So we may miss 1 or 2 treatments, but over time, this calibration mechanism, this validation mechanism should improve the simulator, especially if you're working in a particular asset. You should have, after a few designs, a pretty good model for stimulation. Okay. Now, I think we have about 10 minutes left, or? Okay. So I'll just focus on 2 parts, acid selection and the diverter selection. Okay. The main parameter that is used to identify, or just used for acid selection, is the pore volume of acid to break through. This is the measure of the efficiency of the acid. So the way it's measured is we take a core. It's very much like the core that is sitting over there. We flow acid from one side, right? And we measure the pressure drop. So when there's no wormhole, the pressure drop is high, right? And as the wormhole starts propagating through the core, right, the pressure drop starts decreasing. When it's near 0, that means the wormhole has propagated through the entire core, and this point is called pore volume of acid to break through. Right? Now this pore volume of acid to break through is a function of many variables, and I've listed some of them over here. So it's a function of injection rate, And there's clearly an optimum rate for that you'll get the maximum efficiency of the acid. There's temperature dependence, there's acid type dependence. Acid type, I mean you have organic acids or inorganic acid, chelants, etc. Right? That affect the reaction rate. Then I have acid concentration. So if you decide on acid, then if you decide on a concentration, suppose you decide on a hydrochloric acid, is it going to be 5%, 10, 15, 20, 25? So what is the concentration you're going to use? Then if you decide on the fluid microstructure. So by microstructure I mean fluids like emulsified acid. If you look under a microscope, you see bubbles or droplets of acid in an oil phase, right? So that's microstructure compared to plain acids like just 15% hydrochloric acid. If you look under a microscope, there's no structure to the fluid, right? So foams and emulsified acids have microstructure. So how that microstructure is going to influence the pore volume of acid to break through. Then the mineralogy, is it mostly calcite? Is it dolomite? How much clays do we have in the calcite, etc. And then the pore structure, is it a grain stone? Is it a mudstone? Is it wugs? So all of these parameters influence the pore volume of acid to break through. Okay? I'm just going to go maybe one or two parameters, and this one is on the injection velocity. So I have pore volume of acid to break through, right, on this axis versus injection velocity. What I have on the top colored figure is the simulation result, right? At the bottom is the X-ray of the actual core that was acidized. So if the injection velocity is very low, what I get is a phase dissolution. That means the entire rock has to dissolve before the acid fronts move forward, right? So for this acid front, which is this red over here and this black over here, right, to break through, it has to dissolve the entire rock, 100% dissolution, before it will break through. That's a very inefficient use of acid, right? Compared to something like this over here, where you get a wormhole, a straight, not many branches wormhole, and if you have a good wormhole, thin wormhole long, we only dissolve about 2 to 3% of the rock, right? So the acid can go very deep in the formation compared to here. So if it's 2 or 3% here, 100% over here is 50 times more efficient, right? Okay, so knowing your injection velocity, especially for the acid that you have selected, is really critical in designing and picking the fluid. And this plot shows that it's kind of a busy plot, but what the key thing here is I have the same variable, pore volume of acid to break through versus injection rate, but this is actual data, right? And over several systems here, the key thing is this is a log-log plot, right? This is a log-log plot. This is the only way I could bring them together. And you can see the optimum can be easily an order or 2 orders of magnitude different between the different systems, right? So it's really critical to realize for your particular mineralogy, temperature, what acid, where do you sit on this, and when you're injecting the treatment, is the treatment over here or on this side or that side, right? So it's very important to understand that. The other factor is that influences pore volume of acid to break through is the rock pore structure. So I have about 6 different rock types. From one side, extreme, I have a relatively clean grain stone, right? Nice porosity, mostly accessible. And then it changes all the way to a mudstone, where there's a lot of microporosity, which is not very accessible. Now, so this is your rock pore structure, and I've also shown some fluid structures here. So plain acid, if you look under a microscope, looks still plain, right? This is why it's plain. But here is emulsified acid at 200 times the resolution. What you see here are the droplets of acid. These droplets are about, 10 microns. Go from 6 microns to 12 microns, about 10 microns. And that's about the same order of magnitude as some of these pore structures over here. So when you start injecting a fluid which has a microstructure into a rock which could have different kinds of porosities, how the acid is going to behave and which one is going to be more efficient depends on your rock type and also on the fluid type you select. Okay, I'll skip that. Now, so pore volume of acid to break through measures how much acid you need. I've shown two different rock types over here which have very similar pore volume of acid to break through, right? They're both almost 100% calcite. They were both acidized at the same temperature, 150 degrees Fahrenheit, with the same acid, 15% hydrochloric acid. Same core length, 6 inch by 1.5 inch, right? Everything is same, and the injection rate are also same. But what I want to show is the structure of the wormholes that is so different between these two rock types. So this is the same mineralogy, same acid, everything, but look at the structure of the wormholes, right? In ocean chalk, we dissolve a lot more rock compared to a winterset, which is a grainstone. And why is this important? It's important for the life of the treatment. If you dissolve a lot of rock, right? Chemical diverters, they work at a much lower perm contrast, or I mean, they're after a couple of orders of magnitude, they are not very effective, but operationally they are much lower risk. Right? So the choice is between how much risk tolerance we have, and it's no hard and fast rule. And I've worked with companies where they saw 3 orders of magnitude in perm contrast. They went with mechanical diverters, packers. They got a few packers stuck in some very large wells which were producing, about 100 million scuffs. And then they said, okay, we can't have a well shut in to retrieve the packer. So they went to chemical diversion. They tried chemical diversion for a few years, and they found it was not very effective because they had a very large perm contrast. And the last time I talked to them, they went back to the mechanical diverters. So the choice is basically depends on the risk tolerance and what your targets are. Okay. Okay. I think I'll just show one example, and I think let me skip that. Okay. So this is one example I would like to show. This is more on the evaluation side of the treatment. Right. This is the last step. This one over here, the treatment evaluation, execution, monitoring, and evaluation part. Right. So, and this is all documented in this SPE paper over here. This is an offshore case where the company over here did their homework properly. They a lot of characterization of the rock, they simulated, they designed, and then they basically picked 2 designs that they wanted to take to the field trial. So I'm calling it design 1 and design 2. So design 1 was the favorite going into the field trial. They had about 15 to 20 wells for each design, right? So design 1 had 15, 20 wells, design 2. And the overall production from both of these designs was about similar, right? So the total production was similar, but what I really admire about this company is they took the additional effort and did a flow profile. And the difference really showed up in the flow profile, which I've shown over here. So design 1 was consistently missing this zone over here, while design 2 was able to stimulate that zone. Right? Now it turned out that design 2 was also operationally much simpler. Right? So it was offshore, so it was much lower cost. But they did not know that before going to the field trial. Right? So only by investing the little bit of engineering required, which I think paid off many times over, because it's only a small group of wells but in which did the flow profile, and they discovered a design which is a lower cost and much more effective, and then they could replicate their design for the rest of the field. So yes, it took a little bit of engineering, And it also shows that the simulators are not perfect because this is a very unique kind of carbonate. And the simulators did not have that kind of wormholing models in the simulator. So from their field trials and the recalibration of the simulator, they were able to figure out a design which was actually very good at simulating all the intervals, right? So it really paid itself out. Okay, with that, I would like to conclude. So the main message here is that in my opinion, carbonate stimulation treatments are under-optimized, and the main reason for that is that the success criteria that we have set for carbonate stimulation is too low. Production increase, if we make that as a success criteria, then almost all the treatments are successful, and only drastic failures are re-stimulated, right? Then I talked about some of the common design challenges. Why is it so difficult? So the biggest design challenge is the placement of the acid. I think it contributes to more than 70–80% of optimization, right? The second is the fluid selection, and third is simulation. In the example I showed in which we had a well which went from 300 to 3,000 barrels of oil per day, the first treatment that did not increase in production failed because they could not place the acid, right, to the zone of interest. So the acid never reached that zone, and the production did not increase. So the first of this one was they could not place the acid, right? The second treatment failed because they selected an under-optimized acid formulation. So it was a high temperature. They used hydrochloric acid, which is very inefficient at high temperature, right? So if they had selected the acid properly, so they were able to, in the next treatment, they were able to place the acid, but they did not select the right acid. And if they selected, they would have gotten 6,000 barrels of oil per day, right? And the third one is simulation, right? Just because of lack of resources, it's a very complex problem, but not many resources are devoted to it because all treatments are considered successful, right? Now then I presented a design workflow, which is a systematic way of looking at some of these design variables, and I showed an example, okay?